Hello class and welcome to this video lecture on equilibria of slightly soluble salts, part 1. Okay, salts can be described as being either soluble, slightly soluble, or insoluble. Okay, so if we take a salt and add some water until we get a saturated solution. Okay, now we can tell that this solution is saturated because there is some undissolved solid at the bottom of the beaker. Okay, really we need to answer the question, how much solute is dissolved in the solution? How much of this solid dissolved? And that's going to really determine whether or not we call the salt soluble, slightly soluble, or insoluble. Okay, so what we're kind of focusing on is the concentration of a saturated solution of the salt. So if a salt is considered to be soluble, the concentration of a saturated solution is greater than or equal to 0.1 moles per liter. Okay. A salt that we consider to be insoluble, those salts, the concentration of a saturated solution of that salt will be less than or equal to 0.01 moles per liter. And a salt that is considered to be slightly soluble is going to have a concentration of a saturated solution somewhere between these two values. Okay, it's going to be greater than 0.01 moles per liter, but less than 0.1 moles per liter. So technically, class, these are the guidelines that differentiate among these three descriptive terms here. Now we're going to be focusing on these last two. Okay, when we talk about a salt being insoluble in water or slightly soluble in water, we're going to be dealing with these scenarios right here. Okay, so that's going to be our focus in this topic in this video lecture. Okay, so we're going to look at some calculations, what we call the molar solubility. Okay, so let's consider something like silver chloride. Silver chloride is an insoluble salt. Now, class, by convention, the way we write the equilibria for salts that are slightly soluble or are insoluble, we always put the solid on the left. Okay, so if you think back to that picture where we had the beaker and the undissolved solid at the bottom of the beaker, there's an equilibrium that's occurring between the solid, okay, and the ions in aqueous solution. And so by convention, we always show the solid on the left in equilibrium with its ions. We show the ions on the right. Okay, now this is an equilibrium, so we can have an equilibrium constant. Remember, products over reactants, leaving out what? Solids and liquids, right? Well, since we have a solid here, we wouldn't write that. In other words, that the denominator would really be 1. Okay, now, class, we call this KSP. KSP, and the SP stands for solubility product. So this is called a solubility product constant. Okay, so it's very similar, class, to Kc or Kp, Ka or Kb. Those were all different types of equilibrium constants. The equilibrium constant that we use when we're talking about slightly soluble or insoluble salts, we call that a KSP. Okay, and what do all equilibrium constants depend upon? They're constant as long as what? The temperature's constant, right? So these are constant as long as the temperature's constant. Now, class, there's an appendix in your book where you can look this up. Okay, and if you look up the KSP For silver chloride, you'll see it's 1.6 times 10 to the minus 10. Now, class, if you remember, what was one aspect of all Ka values? They were all small, weren't they? They were all less than 1. Kb values, they were all less than 1. All Ksp values, class, they're going to be small. What does that mean? That means the equilibrium lies to the left, correct? If this is small, what does that mean? These are very, very small, meaning that there's a lot of reactant. Not much of this dissolves, right? That makes sense if it's an insoluble salt, right, or slightly soluble salt. So in reality, a tiny amount of it dissolves, a very small amount, okay? All right, now, class, if you'll recall, in the past when we were talking about acids and bases, we would say, X reacts to give X of this and X of this. Well, we could use the symbol X. Typically, we use the symbol S when we're talking about these salts, and you'll see why in just a minute. Okay, so instead of saying X reacts, I'm going to say that S dissolves. S of this dissolves to give S of this and S of this. Because what? We have a 1 to 1 to 1 mole ratio. So for every 1 mole of this that dissolves, 1 mole of this forms, 1 mole of this forms. Okay? Now these are equilibrium concentrations that we plug into here, class. So what we do is we put S times S, right? We're using values of S here. S times S, or S squared, is equal to the Ksp value. We take the square root of both sides. We get S is equal to 1.3 times 10 to the minus 5. Okay, class, this is what we call the molar solubility. The molar solubility. It is the solubility of the salt in moles per liter. Okay, it is the amount of the salt that dissolves. What did we say? We say S dissolves, right? That's what we said. S dissolves. So the amount of this that dissolves is 1.3 times 10 to the minus 5 moles per liter. Okay, so this is the solubility in moles per liter. Now, the silver ion concentration is S, so we can say that the silver ion concentration is 1.3 times 10 to the minus 5, as is the chloride ion concentration. Okay, so class, when we calculate the molar solubility of silver chloride, this is it. Okay, this is the amount of silver chloride that dissolves in moles per liter. That's not a lot. Okay, so the molar solubility of silver chloride in pure water is 1.3 times 10 to the minus 5 moles per liter. Okay, all right, now what if we wanted to calculate the molar solubility of silver chloride not in pure water, but in a solution that's 3.5 moles per liter of sodium chloride? Okay, so we want the solubility of silver chloride in 3.5 molar sodium chloride. Well, we write down our equilibrium, again, always putting the solid on the left. We write our Ksp value. This doesn't change, right? This is only dependent upon the temperature. Okay. So, class, if this were in pure water, we kind of set it up like we did last time. We said S of this dissolves to give S of this and S of this. That's the scenario that we had for pure water. Okay. Now this problem's a little different. This is not pure water. It's in 3.5 molar sodium chloride. So we've got 3.5 moles per liter of sodium ions, and we've got 3.5 moles per liter of chloride ions. Okay, so we've got to include the 3.5 moles per liter of chloride ions here. In this solution, class, we have two sources of chloride ions. Two sources of chloride ions. We've got the tiny amount that we get from this salt, silver chloride, dissolving, but we've already got some chloride ion that was in the solution. So we've got some chloride from the sodium chloride. We've got a little bit of chloride, the S coming from the silver chloride. Okay, so we put S for the silver ion. We've got S plus 3.5. Okay, now, class, S was small, wasn't it? I mean, S was small on the previous slide. Not much of this dissolves, right? We make a simplifying assumption here, class, that S is very, very small compared to 3.5. That's a good assumption because this value is very small, isn't it? Okay, so we make a simplifying assumption here. Okay, so this changes to S times what? 3.5 is equal to 1.6 times 10 to the minus 10. We solve that for S. We get 4.6 times 10 to the minus 11. Now, class, we would need to check the assumption. Remember, we still use the 5% rule. I'm not going to show the checking of the assumption here, class, but you need to always check the assumption. I'm not going to take the time to do that because you should be very, familiar with that calculation. Okay, so the silver ion concentration is S. The chloride ion concentration is S plus 3.5. What are we going to get when we take this tiny number here, this very small number, and we add it to 3.5? What are we going to get for the chloride? We're going to get 3.5. Okay, so these are the ion concentrations in the solution. And class, this is an example of what we call the common ion effect. Look at the molar solubility, class. The molar solubility is very, very small. Okay, what happens? Look at this equilibrium, class. What happens if we add chloride to this? Remember Le Chatelier's principle? If we add chloride to this, what does that do? That shifts the equilibrium to the left. Meaning what? Less of this is going to dissolve. Okay? When there is an ion in common with this salt that's in the solution, that's going to lessen or lower the amount of the salt that dissolves. Okay? If I have this ion present in the solution, less of this is going to dissolve. Now, class, I'm going to put this next slide. I'm going to put the slide up that we had for the previous problem. The solubility of silver chloride in pure water was 1.3 times 10 to the minus 5. That's small. Not much of this dissolved. But look what happens, class. When we add chloride, what happens to the solubility? It went down. Let me put the previous slide back up there. It went from 1.3 times 10 to the minus 5 to 4.6 times 10 to the minus 11. That's a factor of 10 to the 6th. That lowered the solubility, class, by 1,000,000 times. That is the example, class, of the common ion effect. If we add some chloride, it shifts it to the left. Less of this is going to dissolve. Okay? All right. Let's look at another example. Same type of calculation. Let's use a different salt. Okay? So we want to look at a couple of scenarios here. Let's calculate the molar solubility of lead-2 iodide in pure water and in 0.45 molar lead-2 nitrate. Okay, so let's look at part A first. We want to calculate the molar solubility of lead-2 iodide in pure water. So we write our equilibrium. We put the solid on the left. Okay. For every 1 mole of this that dissolves, right, we get 1 mole of lead 2, we get 2 moles of iodide. Okay. We write our KSP, products over reactants. Excuse me, our reactant is always going to be a solid, isn't it? So our denominator is always going to be 1. So we've got the lead ion concentration times the iodide ion concentration squared. We look this up in the table in the book. We get 1.4 times 10 to the minus 8. All right, so we're going to say S of this dissolves to give what? S of this, and how much of this? Look at this, 2S, right? We've got a 1 to 2 mole ratio. So S and 2S is what we get. Okay. So now let's look at this. We substitute these values in. We put S in for the lead 2. We put 2S. We got S times 2S quantity squared. This would be 4S cubed is equal to 1.4 times 10 to the minus 8. We divide both sides by 4. Take the cube root of both sides of this equation, okay, which would be the same thing as what? Raising this to the 1/3 power. So when you solve that for S, you get 1.5 times 10 to the minus 3. That's S. So S is the lead ion concentration, 1.5 times 10 to the minus 3. What's the iodide? It's twice that amount, isn't it? The iodide ion concentration is 3.0 times 10 to the minus 3. Okay, so what is our answer, class? Our answer is this. It's asking for the molar solubility. What is that? That is the amount of this that dissolves. That's the amount of this that's soluble in what? Moles per liter. Molar solubility. Okay? Molar solubility. All right. Excuse me. Now let's try to solve part B. What is the molar solubility of lead 2 iodide in a 0.45 molar lead 2 nitrate solution? Okay. Well, we start off by writing the equilibrium with the solid on the left. Okay. Now, class, we kind of pretend like, at least starting off, that it's in pure water. It's not. Okay. Of course, KSP didn't change. We still write our KSP expression. So we say S dissolves to give S of this and what? 2S of this. Now this would be if it were pure water, right? It's not pure water. What is it? It's in 0.45 molar lead 2 nitrate. What's the concentration of lead 2 ions supplied by this solution? 0.45. What's the concentration of nitrate ions from this solution? 0.90. Why is it 0.90? Because for every mole of this, we have 2 moles of nitrate. Okay? So when we have this in the solution, we've got 0.45 moles per liter of lead 2 ions. We've got 0.90 moles per liter of nitrate ions. Now the nitrate doesn't affect this, does it? It doesn't participate. But this lead 2 does, doesn't it? So we've got to include this in our concentration of lead 2. So class, there are 2 sources of the lead 2 ion in this solution. There's the tiny amount that we get from this salt dissolving, but then there's some that was already in the solution from the lead 2 nitrate. So we set it up like this. We substitute into the KSP. We've got S plus 0.45. We've got 2S that we substitute in here, 2S quantity squared. Now, class, you know what we're going to do? Simplifying assumption, right? This looks pretty horrendous, doesn't it? If we had to expand all of this out, okay? But we make the simplifying assumption here. We assume that S is negligible compared to 0.45. That makes it a little bit better. So then this becomes 0.45 times 2S quantity squared. Okay. When you solve that for S, okay, you get 8.8 times 10 to the minus 5. I didn't show all those steps there, class, but you expand this would be what, 4s squared, right? 4s squared times 0.45, then you would isolate your s, take the square root of both sides, okay? I think you can all solve that. I'm pretty confident in that. So this is your s value, okay? Now, I didn't show the checking of the assumption, class. You need to check the assumption. 99.9% of the time, class, the assumption is going to be good. As long as these concentrations are pretty high, right? The higher the concentration, the lower the KSP, the better the assumption. Same type of guidelines we had for the assumptions with the acid-base topic that we talked about, okay? All right, so what is the lead concentration? It's going to be S plus 0.45. It's going to be this plus 0.45. Well, that's going to be 0.45 because S is tiny, isn't it? The iodide is going to be 2 times S. So you take this S and you double it. You get 1.8 times 10 to the minus 4. Okay. Now, class, let me ask you something. How could I check this? How could I check my results? I didn't show that. We've seen how we can check the assumption, but how can I check and make sure these concentrations are right? I could plug them into this equation right here, couldn't I? Okay. I won't do that here, but I mean, you can do that. You can substitute both of these concentrations in, see if you get 1.4 times 10 to the minus 8. That's a way you can check yourself, okay? So class, again, this is an example of the common ion effect, okay? This is our molar solubility. Now, class, I'm going to put the previous slide. You remember what it was in pure water? I don't. Let's go back and look. I know it was a lot greater than that, okay? In pure water, how much of this dissolved? 1.5 times 10 to the minus 3, okay? We add some lead-2 ions. What does that do? That shifts the equilibrium. Less of it dissolves. Less of this dissolves. So anytime you have an ion in common with the salt, class, less of it is going to dissolve. That's an example of the common ion effect, okay? All right, so class, what are we looking at here? This is Le Chatelier's principle. Le Chatelier's principle, it applies, right? When you have an equilibrium and you try to stress that equilibrium, okay? So look at this. This is going to be a little bit of a review because that's what this is, class. It's Le Chatelier's principle. So what's going to happen if we add lead-2 ions? What happens if we increase this? We add some more of this. It's going to shift to the left, right? The solubility of the salt decreases. If it shifts to the left, what does that mean? Less of this is what? Dissolving, right? What's going to happen if we add some more iodide? Okay, it's going to shift to the left. And if it shifts to the left, less of this salt will dissolve. The solubility decreases. Okay? What if we removed some lead-2? What if we had this equilibrium and we removed some of this? What's going to happen? The equilibrium will shift to the right. And what? More of this will dissolve, right? The solubility of the salt increases. If this shifts to the right, more of this solid will go into solution. Okay? What's going to happen if we remove some iodide? What will happen? It's going to shift to the right. It's going to shift to the right, and the solubility of the salt is going to increase. Okay? Now, class, as it turns out, this is going to have more of an effect than this. Because in the KSP expression, this concentration was squared, wasn't it? This concentration was to the first power, but this concentration was squared. So the iodide ion concentration is going to have more effect on the solubility when we start, trying to shift the equilibrium one direction or the other. This is going to have more effect on the solubility than this. Okay? Well, class, this kind of starts our discussion, our lecture, uh, with slightly soluble salts. We've looked at calculating the molar solubility of a salt in water. We've looked at calculating the molar solubility of a salt in a solution containing what? Ions in common with the salt. And we've seen the application of Le Chatelier's principle. So class, I hope that you have found this video lecture to be very helpful in your understanding of some of these concepts. We're going to continue our discussion of slightly soluble salts.